Now let us extend the properties of causality that we have learned for anti-causality and non-causality as well. Let us consider the continuous time systems case. If the discrete time LTI system, if the continuous time LTI system of impulse response h of t is causal, then h of t is equal to 0 for t less than 0. If the continuous time system is anti-causal, then h of t is equal to 0 for t greater than or equal to 0. If the continuous time system is non-causal, then h of t is not equal to 0 for at least one t1 less than 0 and for at least one t2 greater than 0. So based on these properties of the impulse response, we can say if the continuous time system is causal or anti-causal or non-causal. Now let us consider a discrete time LTI system. If the discrete time LTI system of impulse response h of n is causal, then h of n is equal to 0 for n less than 0. If the discrete time LTI system is anti-causal, then h of n is equal to 0 for n greater than or equal to 0. We say that the discrete time LTI system is non-causal if h of n is not equal to 0 for at least one n1 less than 0 and for n2 greater than 0. So from this property of the impulse response, we can say if the discrete time system is causal or anti-causal or non-causal. Let us consider some examples now. Suppose there is a continuous time LTI system of impulse response sine of 2t ut. We see that h of t is equal to 0 for t less than 0. From this we see that the discrete time LTI system is causal. Now let us consider other continuous time system, a continuous time LTI system of impulse response. H of t is equal to e power minus t multiplied by u of u of minus t. We see that in this case h of t is equal to 0 for t greater than 0. From this we see that the system is non-causal and not anti-causal as well. The system is non-causal as h of t is not equal to 0 for t less than 0. The system is not anti-causal as h of t is not equal to 0 for t greater than or equal to 0. Please note the equality sign. From this we say that the given system is not causal and not anti-causal as well. Now let us consider another discrete time LTI system of impulse response h of n is equal to minus 3, minus 2, minus 1, 0. Now here the value 0 corresponds to the instant n is equal to 0. Here we see that h of n is equal to 0 for n greater than or equal to 0. So from this we see that the given system is anti-causal. Now let us consider another impulse response, that is h of n is equal to minus 3 comma minus 2 comma minus 1, where the value of minus 2 corresponds to the instant n equal to 0. Here we see that h of n is not equal to 0 or n is equal to 1 comma minus 1, means there exists at least one value of n for n greater than 0 and n less than 0 for which h of n is not 0. From this we see that the given LTI system is non-causal and it is not anti-causal as well. So using these properties, we can say given impulse response of a LTI system, if it is causal or anti-causal or non-causal or non-anti-causal case. Now let us look into another property of the LTI system, that is stability. Given a LTI system of impulse response which of n, the output y of n is equal to sigma k equal to minus infinity to plus infinity x of k multiplied by h of k multiplied by x of n minus k. We have to check the BI/BO stability of this system. Let us assume the input to the LTI system is bounded, that is mod of x of n is less than or equal to bx, where bx is finite. From this we can say that mod of y of n is equal to mod of sigma k equal to minus infinity to plus infinity h of k multiplied by x of n minus k. We know that this is less than or equal to sigma k equal to minus infinity to plus infinity mod of h of k multiplied by mod of x of n minus k. This is because of the relation that mod of a plus b is less than or equal to mod a plus mod b. But we know that mod of x of n minus k is less than or equal to bx. This is because input to the LTI system is bounded. From this we can write that mod of y of n is less than or equal to sigma k equal to minus infinity to plus infinity mod of h of k multiplied by bx. For the given LTI system to be stable in BI/BO sense, this should be less than or equal to by, where by is finite. So this should be satisfied for every n. For this to be satisfied for every n, we can say that sigma k equal to minus infinity to plus infinity mod of h of k should be finite. That is sigma k equal to minus infinity to plus infinity mod of h of k should be less than a value, or we can say that this should be finite for the given LTI system of impulse response h of n to be stable in BI/BO sense. From the above, we see that a discrete time LTI system of impulse response h of n would be stable in BI/BO sense if sigma n equal to minus infinity to plus infinity mod of h of n is finite. Now, similarly, a continuous time LTI system of impulse response h of t is stable in BI/BO sense if integral minus infinity to plus infinity mod of h of t is finite. So these are the conditions that should be satisfied for a continuous time or discrete time system to be stable in BI/BO sense. Now let us consider some of the examples in which the first impulse response of a discrete time system is given as h of n is equal to 1 comma 0 comma 1 comma minus 2, where the value of 1 corresponds to n is equal to 0. Here, for checking the BI/BO stability, we have to find sigma n equal to minus infinity to plus infinity mod of h of n. So this is equal to 4. As it is finite, we see that the given LTI system of impulse response h of n is stable in BI/BO sense. Now let us consider another discrete time LTI system of impulse response h of n is equal to sine of 2n multiplied by un. Here we see that sigma n equal to minus infinity to plus infinity mod of h of n tends to infinity, because sine of 2n is a waveform which sine of 2n multiplied by un is a waveform which is present from 0 to infinity, alternating between the values minus 1 and 1, and because of which the sum sigma n equal to minus infinity to plus infinity mod h of n tends to infinity. So the system is not stable in BI/BO sense. Now let us consider another LTI continuous time LTI system of impulse response h of t is equal to e power minus t into u of t. Here, for the system to be stable, integral minus infinity to plus infinity mod of h of t dt. Sorry, here dt should be present. Finite should be finite. So integral 0 to infinity e power minus t into ut. If we find out this is equal to 1. So as integral minus infinity to plus infinity mod of h of t is finite, we see that the given continuous time LTI system is stable in VIBO sense. Now let us consider another LTI system, continuous time LTI system of impulse response. H of t is equal to e power 2t multiplied by ut. Now if we try to find out integral minus infinity to plus infinity mod of h of t dt, this is equal to integral 0 to infinity e power 2t dt. This is equal this integration, if we try to find out, tends to infinity. So we see that the given continuous time LTI system is not stable in BIBO sense. Now let us start considering, oh sorry, now let us consider another property of the LTI systems, that is invertible LTI system. Given a continuous time LTI, given a discrete time LTI system of impulse response h of n, if there is an input x of n given to the system, let the output be y of n. If this output y of n is fed to another system, say hi of n, if we are able to recover the input x of n completely, we say that the given LTI system of impulse response h of n is invertible. That is, for the given LTI system to be invertible, h of n convolved with hi of n should be equal to delta of n. So, if given a discrete time LTI system of impulse response h of n, if there exists a hi of n such that h of n convolved with hi of n is equal to delta of n, we say that the given LTI system is invertible. Similarly, in case of continuous time systems, if we are able to find continuous time LTI system of impulse response h of t, if we are able to find hi of t such that hi of t convolved with h of t is equal to delta of t, we say that the given system is invertible. So block diagram wise, this can be represented as x of t is the input to a LTI system of impulse response h of t, and the output of the LTI system is y of t, which is fed to another LTI system of impulse response hi of t. Here we get an output, say z of t, which is equal to x of t. Then we say that the given LTI system of impulse response h of t is invertible, and hi of t is the impulse response of the inverse system. Now let us look into different ways of representation of continuous or discrete time systems. We know that a continuous or discrete time system is represented by the transformation. Example, y of t is equal to sine of x of t, and another way is y of n is equal to x of n multiplied by x of n plus 3. If the continuous or discrete time system is LTI system, that is, it is a special case of continuous or discrete time system. In this case, the system can be represented using transformation. Example, y of t is equal to x of t plus 1, and another way is y of n is equal to x of n plus x of n minus 2. Another way of representing LTI systems is using the impulse response h of n or h of t, where the impulse response is the response of the LTI system for impulse input. Another way of representing the system is by LCCDE, that is linear constant coefficient difference equation. The general form of the same can be written as sigma k equal to 0 to n ak into y of n minus k is equal to sigma m equal to 0 to m bm multiplied by x of n minus m, where ak and bm belong to R. For example, y of n minus half multiplied by y of n minus 1 is equal to x of n plus 1 by 3 x of n minus 1. This is the example of a LCCDE, that is linear constant coefficient difference equation. We are discussing this in the context of discrete time systems. Another way of representing a LTI system is by using system function, that is h of e power j omega or h of z. The obtaining the system function h of e power j omega or h of z will be discussed in the later parts of this session or in the later parts of the signals and systems course. So from this we see that given a generic continuous or discrete time system, it can be represented by its transformation. If the system is LTI, that is, it is a special case of continuous or discrete time system. In this case, the system can be represented by the transformation or impulse response or LCCDE or the system function along with ROC. Now, consider a discrete time system whose unit step response is given as yu of n, where unit step response means response of the discrete time system for unit step input. In this case, impulse response of the system is given as h of n is equal to yu of n minus yu of n minus 1. If the system is continuous time system and if yu of t is the unit step response of the system, that is response of the system for unit step input. In this case, the impulse response of the system is given as h of t is equal to dyu by dt. Let us look into this using an example. Suppose there is a discrete time system whose unit step response is yu of n is equal to 0, 1, 2, 3, where 0 corresponds to the instant n is equal to 0. In this case, the impulse response is given as h of n is equal to yu of n minus yu of n minus 1 using the formula marked. In this case, the response is given as 0 minus 0, which corresponds to the instant n is equal to 0, 1 minus 0, 2 minus 1, 3 minus 2, and 0 minus 3, which can be simplified as 0, 1, 1, 1, minus 3, where the value 0 corresponds to the instant n is equal to 0. Similarly, if unit step response of a continuous time LTI system is given as yu of t is equal to sine of 2t. In this case, the impulse response is given as h of t is equal to dyu by dt. This is equal to 2 cos 2t, which is a derivative of sine 2t. From this, we see that given the unit step response of a continuous time or discrete time system, its impulse response, that is h of n or h of t, can be obtained uniquely. Now let us look into another topic related to LTI systems, that is response of LTI systems for sinusoidal input. Let us consider a discrete time LTI system of impulse response h of n. Let the Fourier transform of h of n be h of e power j omega if there is a input of x of n is equal to a into e power j times omega n plus phi is given as input to the system. Let y of n be the output of the system. In this case, the output y of n can generically be written as a times magnitude of h of e power j omega e power j times omega n plus phi plus phase of h of e power j omega. So from this we can say that if there is a sinusoidal input given to the system, the magnitude gets scaled by the magnitude of the frequency response at omega, and phase gets shifted by phase of the frequency response at omega. So from this we can say that the new output y of n will have a magnitude scaled by magnitude of h of e power j omega, and a phase of the y of n will get shifted by phase of h of e power j omega. Now let us consider similarly a continuous time system. X of t is equal to a into e power j omega t plus phi, which is given as an input to the LTI system of impulse response h of t. If y of t is the output of the LTI system, in this case the output is given as the output of the y of t can be obtained from Fourier transform of h of t, which is equal to h of j omega. So y of t is equal to a times magnitude of h of j omega multiplied by e power j omega t plus phi plus phase of h of j omega. From this we see that the magnitude of y of t gets scaled by magnitude of h of j omega, and phase of y of t gets shifted by phase of h of j omega. From this we see that given a sinusoidal input to a LTI system, we can obtain the output y of t from the frequency response of the LTI system. Now let us solve some of the problems related to the theory that we covered as a part of the LTI system. There is a discrete time system of impulse response h of n is equal to -1, 1, 2, 3, where the value 1 corresponds to the instant n is equal to 0. We have to characterize the system based on causality, memoryless property, stability. Here we see that for the given impulse response, h of n is not equal to h of n is not equal to 0 for n less than 0. So from this we can say that the given system is non-causal, because for a system to be causal, h of n should be equal to 0 for n less than 0. So for deciding the stability of the system, find out sigma n equal to minus infinity to plus infinity mod of h of n, which is equal to 7. From this we see that the given system is stable in VIBO sense. We also see that h of n is not equal to 0 for n not equal to 0. From this we see that the given system is not memoryless, or the system has memory. Now let us consider another problem as related to the LTI systems. It's given that the unit step response of a LTI system is given as yu of t is equal to e power minus t into u of t. So we have to find the impulse response of the LTI system. We know that the impulse response of a LTI system can be obtained from the unit step response as h of t is equal to dyu by dt. This is equal to minus e power minus t u of t. Now, in the next problem, there are three systems given in the options A, B, and C. They are 1 by 2 whole power n u of n, and the option B corresponds to minus 2 power n u of minus n minus 1, and the option C corresponds to 3 power n into u of n. We have to find which of these options corresponds to, or all the three options given corresponds to impulse responses of LTI systems. We have to find the system for which we have to find the system which is causal and unstable. Now let us consider the system in option A. We see that the impulse response is given as 1 by 2 whole power n multiplied by u of n. So here we see that the impulse response h of n is equal to 0 for n less than 0. From this we see that the system is causal. We also see that sigma n equal to minus infinity to plus infinity mod of h of n can be written as sigma n equal to 0 to infinity 1 by 2 whole power n, which upon simplifying using the infinite series sum formula can be reduced as 2. As the summation is finite, we see that the system is stable in BSBO sense. Now, so this is not the required one. Now let us consider the system in option B. Here we see that the impulse response is minus 2 power n u of minus n minus 1. From this we see that the impulse response h of n is equal to 0 for n greater than or equal to 0. So the system is anti-causal and hence non-causal. Also we see that the infinite sum sigma n equal to minus infinity to plus infinity mod of h of n, if found out, is finite. From this we see that the system is stable in BIBO sense. Now finally if we found out the system in option C, finally if we pick the system in option C, that is 3 power n into u of n, here h of n is 0 for n less than 0. From this we see that the system is causal. Also if we find out sigma n equal to minus infinity to plus infinity mod of h of n, we find that the summation tends to infinity. So from this we can say that the system is not stable in BIBO sense. From this we see that this is the required system. Please note that the system in option B is also not the required system. So here we need to find out the causal and unstable system out of the three options given, and we see that 3 power n into u of n corresponds to the system. 3 power n into u of n is the impulse response of the system, which is causal and not BIBO stable. So from this we see that the correct option is C. Now let us consider another problem in which there is a LTI system of impulse response h of n, to which there is an input of x of n given. It's given that the output of the LTI system is y of n is equal to n into u of n. Now there is another LTI system of impulse response x of n minus 1, which is given an input of h of n. We have to find the output of the LTI system, that is y2 of n. From the above we see that x of n minus 1 can be represented as, sorry, from the first system we see that y1 of n can be represented as x of n convolved with h of n, which is equal to n into u of n. Also we see that y2 of n can be written as x of n minus 1 convolved with h of n, but we know that x of n minus 1 can be represented as x of n convolved with delta of n minus 1. So this can further be written as delta of n minus 1 convolved with x of n convolved with h of n. So this is by using the commutative property. So this can further be reduced as using the associated property delta of n minus 1 convolved with y1 of n, because we know that x of n convolved with h of n is equal to y1 of n. So we know that delta of n minus 1 convolved with y1 of n is equal to y1 of n minus 1. But y1 of n is n into u of n. So this can be simplified as n minus 1 into u of n minus 1. So from this we see that the output of the second LTI system is y2 of n is equal to n minus 1 into u of n minus 1. Suppose there is a LT. Now let us consider another problem in which the impulse response of the LTI system is given as h of n is equal to minus 1 whole power n into u of n. We have to find if this system is stable, memoryless, or causal. From the impulse response, we see that the h of n is equal to 0 for n less than 0. So we see that the discrete time system is causal. Also, we see that sigma n equal to minus infinity to plus infinity mod of h of n is tends to infinity. So as the sum is not finite, we see that the system is not BIBO stable. That is, the system is not stable in BIBO sense. Now, finally, we see that h of n is not equal to 0 for n not equal to 0. From this, we see that the system has memory. So, the given LTI system with impulse response h of n is equal to minus 1 whole power n is causal, not BIBO stable, and has memory. Now, let us consider another problem related to LTI systems. Suppose there is a LTI system which is described by the input output relation y of n minus 1 by 2 y of n minus 1 is equal to x of n minus 1. We have to find the output of the system for an input of x of n is equal to 1 comma 3 comma 0 comma minus 1 if it is given that y of minus 1 is equal to 0. Please note that the value of 3 corresponds to the instant n is equal to 0. For finding y of n, first substitute n is equal to 0. It is given that y of minus 1 is equal to 0. From this we see that by substituting n equal to 0 in the LCCD, we see that y of 0 minus half y of minus 1 is equal to x of minus 1. But x of minus 1 is 1. So this can be written as y of 0 is equal to 1. Similarly, upon substituting n is equal to 1 in the LCCD, we see that y of 1 minus half y of 0 is equal to x of 0. But we know that x of 0 is 3 and y of 0 is 1. From this, we see that y of 1 is equal to 3 plus 1 by 2, that is 7 by 2. Similarly, upon substituting n is equal to 2, we see that y of 2 minus half y of 1 is equal to x of 1. From this, we see that y of 2 is equal to 7 by 4 plus 0 because it is given that x of 1 is 0 and y of 1 is 7 by 2. So this is equal to 7 by 4. Similarly, upon substituting n is equal to 3, we see that y of 3 minus half y of 2 is equal to x of 2. But we know that y of 2 is 7 by 4 and x of 2 is minus 1. From this, we see that y of 3 is equal to half into 7 by 4 minus 1. So this upon simplifying becomes minus 1 by 8. Finally, upon substituting n is equal to 4, we see that y of 4 minus half y of 3 is equal to is equal to x of 3. We know that x of 3 is 0 and y of 3 is minus 1 by 8. From this, we see that y of 4 is equal to 1 by 16. So if we go ahead, similarly, we see that y of 5 is equal to y of 6 is equal to and so on is 0. From this, we see that by using the given LCCDE, the output of the system can be written as y of n is equal to 1 comma 7 by 2, 7 by 4, minus 1 by 8, 1 by 16, 0, and so on. And the value of 1 corresponds to the instant n is equal to 0.